Parte, talking about wives, S7 AGN survey. You hear a noise when you have still 5 minutes.
Okay. So I would like to thank the organizers for inviting me to talk about the WIFES S7 AGN survey, and I'll try to get that in full. So it's a Siding Spring Southern Seaford spectroscopic snapshot survey, and I will go fully 3D in this talk because it's based on optical integral field spectroscopy, and the main aim of the survey is to study the AGN narrowline region. And here I've just listed the collaborators, which are part of the paper describing the survey led by Mike Doppiter, which has been submitted earlier this month. So just a brief overview over the project. It's, as the name says, a snapshot survey of about 140 nearby Seaford galaxies done in 3D spectroscopy. And the target selection is largely based on the Véron-SETI and Véron quasar catalog. We have biased the sample towards radio-detected sources. So at least where NDSS fluxes, for example, are available, typically fluxes larger than 20 millijansky at 20 centimeter. And the sources are largely more nearby than a redshift of 0.02 in order to obtain spatial resolutions, physical spatial resolutions of about a few hundred parsecs on the host galaxy. They are largely, well, obviously southern sources, and generally we try to avoid too high galactic extinction in the galactic plane. And I should also mention that there has just been completed a radio follow-up of 17 of these sources at the GMRT. So this is not a complete sample, but it is a relatively large representative sample of nearby radio-detected AGN. A bit more about the observations and the data themselves. So I said it is based on optical integral field spectroscopy, and the data have been obtained with the wide field spectrograph, also called WIFES, which is located at the 2.3 meter telescope of the Australian National University at Siding Spring. WIFES is operating in an image slicer design, so the incoming light is detected through 25 slitlets, which have 1 arcsecond width and 38 arcsecond length, resulting in a total field of view of 25 by 38 arcseconds. And this is basically the field of view we have for the snapshot survey, centered on the active nucleus of the galaxies. But I will also show a few examples actually where we have several more fields on the galaxies. The detectors themselves have 1 by 1 arcsecond pixels, which is basically adjusted to the seeing conditions which are typically available at Siding Spring of roughly, let's say, 1.5 arcsecond. WIFES has the additional advantage of providing a very wide wavelength coverage because it detects simultaneously through a blue and a red arm. And for this particular project, we are using a fixed setup of a grating of 3000 spectral resolution in the blue and 7000 spectral resolution in the red. This is actually quite high compared to, for these kind of data, 7000 in red, to do kinematic studies. And just briefly, the data reduction is quite straightforward. Meanwhile, there is a Python-based pipeline, which has been described in a paper by Mike Childress earlier this year for WIFES data in general, not just for this project. So this is a rather homogeneous data set of a representative sample of these radio-detected nearby AGN that we get. So just a brief overview over the typical data products that we get. We have seen a few of these already related to the manga survey, for example, earlier this week on Tuesday. We also get the nuclear spectra, but not just, because it's 3D spectroscopy. So for example, and these are not all the same objects, it's just an example slide. We can do gas velocities, investigate gas kinematics, also stellar velocities based on the underlying absorption lines. And then, of course, we have these wide range of various diagnostic lines that can be investigated, for example, to study excitation mechanisms for the gas, as here in 3 color images, if you color the lines, or in line ratio maps to resolve spatially variations in the excitation mechanisms, and what we have also briefly seen earlier this year in these classical BPT diagrams in which 2 line ratios are plotted against each other, and there have been classification schemes, for example, by Kaufmann et al. And Cooley et al. To classify based on the location of these line ratios in this plot into H2 region dominated excitation, AGN or shock dominated excitation, and then there's this intermediate region which is called often composite type excitation. And this is also, I should mention this again here, because in 3D spectroscopy it is a pixel by pixel based BPT diagram, so spatially resolving the excitation in these galaxies. The key science drivers of this project, as the title said, is the AGN narrowline region. And since this is a bit more of a general audience, I've just done my personal, very basic sketch to explain the AGN narrowline region. So this is basically the extended gas, more extended gas in the host galaxy affected by the AGN in a more general sense, either by photoionization or by the radio jet from the AGN, or also by through outflows from the nuclear region. And the narrowline region is typically, these are clouds of sufficiently low densities, so the narrowline region spectrum is characterized by also forbidden lines, because the densities in these clouds are low enough, below the critical densities of these lines, but also permitted lines, in contrast to this high density and high velocity clouds in the broadline region, in the typically inner 1 parsec of an AGN, where you see normally broad permitted lines. And actually narrowline region is a bit of should be maybe a relatively narrowline region, because the lines are not as narrow as those you would see probably from star forming regions in the host galaxy, but they are narrower than the ones of the broadline region. The narrowline region is also in this classical unification scheme by orientation, the region of basically AGN interaction with gas, which is common to all type of AGN. So because it's outside this obscuring material which may obscure the broadline region for certain lines of sight for the observer. So lines from the narrowline region, typical lines like, for example, forbidden O3 emission, have been used to measure AGN strength in a more common way for all types of AGN. So understanding the properties, the physical properties of the narrowline region is actually interesting in various aspects. And I should also mention we are also looking into looking into the nature of liner galaxies. These are low ionization nuclear emission line regions, as originally classified by Heckman, and their major ionization mechanism has been a bit of a debate, because there are various mechanisms, for example, photoionization by the non-thermal continuum of the AGN, or shocks, or hot stars, or post-AGB stars, which could produce these strong low ionization lines seen in liner spectra. And we have some liners in this sample, so this is also one of the aspects we are studying. So for the second part of the talk, I will just go through some of these examples of science I have just outlined briefly, and I will show some first examples from data from this survey for these particular science cases. So I will start, this is more of an advertising slide, I guess, with just a gallery of some of these 3 color images highlighting the extended narrowline regions in some of these objects. So here, these images are colored by line emission. O3 is shown in blue, H alpha in red, and N2 in green. So basically the extended narrowline region would be visible as this bluish turquoise color, and then you have star formation in the host galaxies, which shows as golden or golden to reddish colors in these objects. And you see, just based on this smaller sample of objects, that there is a large variety of morphologies of extended narrowline regions mixing with star formation in the circular nuclear environment of an AGN. So we can also study kinematics, as I mentioned. And here I'm showing one example for the quite well-known C2 galaxy 6300, for which we have obtained 6 fields, as located here. This galaxy has been studied previously in kinematics using H-alpha Fabry-Perot observations, and here you see the large-scale kinematic field by Buta and collaborators. And what they found actually is that the central H-alpha emission, which may be a bit hard to see, is blue shifted by about 100 kilometers per second with respect to the general systematic velocity expected. And very recently there has been a paper by Davies and collaborators looking with symphony into the very nuclear region of this galaxy in molecular hydrogen emission. And they found that the molecular hydrogen emission velocity field has a part of disk rotation plus a biconical outflow, which I've just reproduced here from the image in which they subtracted a disk model from the velocity field to better enhance this biconical outflow here. So there are some indications of possible outflow from the nucleus in this source. And here I'm just showing the S7 Weiss view now, which kind of fills in the intermediate region between these two studies and also provides this large range of diagnostic lines over the full wavelength range we observe. And this is a simple subtraction of stellar velocities from the gas velocities, and you see that also we see this blue shifted about 100 kilometers per second gas with respect to the stellar velocities in the center. And there's also some extension of more blue shifted gas in this larger scale area here. So we cannot just look at it in kinematics, but also look at line width and, as I said, line ratios, which may indicate excitation mechanisms. And here you see the N2 line width, which also shows this increased line width over a larger area in the central part of this galaxy. And on the right-hand side, the O3 over H beta ratio and the N2 over H alpha ratio, particularly, where you also see increased line ratios in this area. So this may indicate some possible relation to this nuclear outflow where you have maybe turbulent gas, maybe shock gas. O3 over H beta, just as a side note, is actually hard to do in this galaxy because it's quite highly extinguished. That's why there's not so many data points in this plot here. Another galaxy with very interesting gas versus stellar kinematics is this prototypical LINA galaxy, NGC 1052. And here you see the Weiss data for the H-alpha velocity field, the H-alpha velocity dispersion, and the stellar velocity field and velocity dispersion. And you will realize that the gas velocity major kinematic axis is basically perpendicular to the major kinematic axis in the stellar velocity field. And furthermore, there's this area of high velocity dispersion which can be seen along this axis or these kind of cones here. This galaxy has been studied earlier also in higher spatial resolution data, and I'm just showing one plot here. This is an integrated O3 image of a study looking at O3 kinematics at sub-arcsecond resolution. And they found basically that the O3 again shows a part of disk rotation plus a high velocity outflow, which in direction is kind of associated with this radio jet known for this object. So an interpretation is that these is actually outflow along the minor axis of this galaxy, and if not just caused by overlap of these outflowing bubbles, this high velocity dispersion could be related to this disk rotation part and possibly be gas that is accreting onto the center and being shocked in this accretion process and therefore producing these high and more turbulent line widths. And this interpretation would lead to just a schematic picture shown here, where on arcsecond scales the jet is actually misaligned with the accretion disk, and this could suggest a double shock scenario for the line emission we see from this object, in which the gas is first shocked in an accretion shock, the incoming gas here, to higher densities, and then there is the jet and its cocoon shocking the gas in a second step, plus some pre-ionization from the nucleus. And when working this out in an ionization model, this reproduces quite well what has been known from optical to UV spectra for this liner, that there's two density components. This had been previously also discussed in a photoionization model by Gable et al., which required two density components and two ionization parameters. So this model would somehow put this on a more physical basis to why there are these two density components in this object. So now I will slightly switch the topic to, in this case, using the narrow-line region in order, as a kind of screen, in order to fingerprint the AGN ionizing continuum. So this can be done in the S7 survey, for example, by taking a model, or by producing a model of now the photoionized narrow-line region, where this is applicable, and then getting information about the actual ionizing continuum, so the EUV to maybe 10 keV AGN ionizing continuum of this narrow-line region gas. So what also goes into this model is the ionization parameter and the chemical abundance of the narrow-line region. And it's much better to, it's much easier to constrain the AGN ionizing continuum in this modeling approach if there was a pre-known value for the chemical abundance of the narrow-line region. And what we are doing is to use abundances which are taken from the H2 regions in the host galaxy and to extrapolate these to the narrow-line region, and so to basically eliminate one of the free parameters in this modeling approach. And I'm showing one example here. Again, a galaxy for which we have 6 fields, but I will come back to the nuclear field in a second. This is another CFA2 galaxy, NGC 5427. It's in an interacting pair actually with NGC 5426. And here you see in grayscale the H-alpha flux of this galaxy, and then in the overlay, the colored data points are the derived chemical abundances from the H2 regions in this galaxy. And basically this shows a very nice gradient, which is here in a radial plot shown in a deprojected radial plot. And based on this then we can extrapolate a value for the chemical abundance of the narrow-line region. This in turn is then used to produce photoionization models of the narrow-line fluxes we get for the various diagnostic lines shown here. And with this basically fixed parameter plane now of the chemical abundance, the model for the AGN ionizing SED, which is represented here by basically the accretion disk plus a hard X-ray part, can be constrained much better and produces these kind of output parameters for the best fitting model in this case. This galaxy is also interesting in terms of when investigating, for example, the mixing of the extended narrow-line emission with star formation. And this is just, again, the classical BPT diagram I'm showing here. And this is showing this galaxy for which we had this narrow-line region model just in the previous slides. And here we are looking at pixel by pixel line ratio values, which are typically in this region which is called composite in the BPT diagrams. And in this case, this can be explained as a mixing between an invariant spectrum of the extended narrow-line region with increasing contribution from the H2 regions, where I show these 2 anchor points here from this study. You see here the fractions increasing. Well, actually it's in the narrow-line region fraction, so the fraction of the narrow-line region to the background H2 region increasing this way. And this also fits quite nicely with what is shown in color here, that is the distance from the AGN. So with increasing distance from the AGN, the contribution from the extended narrow-line region in relation to the contribution from background H2 region decreases. We can also have a look now in the nuclear snapshot of this galaxy into where these line ratios are located spatially, because we have the 3D data. So this here is just colored as O3 to H beta ratio, and this is the nuclear snapshot with the H alpha contours as overlay. And you see that these composite type line ratios, which could be explained as a mixing between the extended narrow line region and the background H2 region contribution, showed some extension, some artifact from the PSF probably, but also some extension at our spatial resolution, which may be an indication, a more subtle indication of an extended narrow line region in this object. So I'll just briefly conclude what I said. So this S7 survey provides a rather homogeneous data set in 3D spectroscopy for a representative sample of local radio-detected AGN. It also, as I've shown in a few examples, provides insights into morphology, excitation and kinematics of the AGN narrowline region at our resolution of about a few hundred parsec scales. And also to note that there is this rather high spectral resolution in the red, which can be used to study kinematics or kinematic components in more detail. There's a way, for example, which I've shown to use the narrowline region as a screen to get further constraints on the actual AGN ionizing continuum, and this sample also serves as a good basis sample to understand the role of the jet-gas interaction in this object, as well as perhaps to gain more insights into the nature of nuclear liner emission. Thank you.
Questions? Please.
That's very nice data. I wasn't entirely clear. I understood your interpretation of the outflow. So what you seem to be seeing was a rotation pattern in the gas, and you were saying this was you interpreted this as outflowing gas.
In the Liner galaxy, or?
Yeah, so you had this case of stellar rotation and gas rotation where...
Yes. So I think there was a Liner galaxy, yeah. This one?
Right, so the upper left, so that's gas velocity, which looks like rotation decoupled from stellar velocity, right?
Yeah.
Well,
and then you were saying you interpret this as outflow. I mean, to me, maybe I would just say it's a huge gas disk that rotates, but that's not your interpretation of this.
So the interpretation was based, you have to see this in context with the other data, so there's more higher resolution data. For example, this study by Sugai and collaborators looking at, at O3 in particular and kinetics at higher resolution. And this is, because it's known that there is this high velocity outflow at smaller scales in relation to the jet. The interpretation is basically based on this idea that there's a larger scale outflow continuing on the larger scales we are covering at the widest resolution along the minor axis of the galaxy itself, the elliptical galaxy.
But still, isn't this rotation? I mean, what do you see in the upper left panel? Isn't this rotating gas?
Just see something that it's approaching and something is receding. Give me something like that.
It could be.
But
In this one, it could be both, I guess.
There is no yellow.
Maybe
It's
the
kind
point
of.
is where is the minor axis of the galaxy?
So this was the minor axis is actually like this. Well, the stellar rotation field is like this, right? The major kinematic axis. So it's basically along the minor axis, and that would support the outflow scenario, I guess.
So, thank you, and now we will hear about variability selected AGNs in the VSP survey of the Cosmos and CDFS regions by Demetra Di Cicco. Sentirai un bip bip quando mancano 5 minuti.
Hi everybody, my name is mattinata. I was one of Massimo Capaccioli's students. Now I am a first year PhD student and I work under the supervision of Maurizio Paolillo and Giuseppe Longo here in Napoli. I am going to illustrate you the results of two works based on optical variability of active galactic nuclei. One of the works was led by me, while the other one was led by Serena Falocco, who is here in the audience and also has a poster here on panel 2. Here is a list of the people who collaborated, who are part of our works. So we all know that most galaxies, probably whole galaxies, host a supermassive black hole in their center, and at some point in their lives they go through an active phase. It is also well known that there is a correlation between some physical properties of the host galaxy and some of the properties of the black hole. This means that AGNs play a relevant role in the framework of galaxy evolution, and of course this is only one of the reasons why we want to go deeper into the investigation of this topic. There are several techniques which are widely used to identify AGNs, and generally a single one is not enough because of different selection effects and biases. I reported here a few ones. For instance, spectroscopy proves useful when we want to select AGNs with spectra characterized by very prominent emission lines. But if this is not the case, that is, if the AGN spectrum is characterized by weaker lines, which depends on viewing angle, spectroscopy becomes challenging, so we need alternative techniques. Generally, we consider X-ray emission as the most reliable indicator of the active nature of a galaxy. So there is a large amount of diagnostics based on the X-ray properties of AGNs. But of course, in order to use X-ray data, we need X-ray observatories, which are generally much more expensive than ground-based telescopes. And moreover, they are characterized by limited fields of view. So again, we need some more techniques. And there is another class of diagnostics which makes use of color to select different sources. Since objects of a different nature have different spectral energy distributions, this reflects into color, and so we can use color to separate different objects according to their nature. But if an AGN is dominated by the light contribution from the host galaxy, color is not suitable for selection. One more technique is based on variability, since it is proved that variability is a defining property of AGNs at all wavelengths, with timescales and amplitudes depending on the observing waveband. Nowadays, we generally attribute variability to changes in the accretion rate and instabilities in the accretion disk. In our work in particular, we focused on optical variability, which has typical timescales of the order of days. Optical variability has already been used in different multi-epoch surveys to identify AGNs. Generally, it allows to retrieve those sources, those AGNs, which are missed by other surveys. For instance, AGNs with an unusually low X-ray emission that cannot be detected in the X-rays. In our work, we have at our disposal data from the BLT survey telescope. I will spare you the description of the telescope since we already heard about it. Our analysis concerns data from a supernova survey, Sudare, which was introduced yesterday by Maria Teresa Botticella. In particular, in my work, in the work which I led, we focused on the cosmos field, and we had at our disposal a 1 square degree area, while in the other work led by Serena, the surveyed area is the Chandra Deep South, which in this case is doubled, and there are two more square degrees to come for the analysis. Anyway, in both cases, we have a baseline of less than 6 months, and the observations were made in several wavebands, but we chose to use R-band data because of the higher observing frequency. Here you can see the cosmos field as imaged by the VST, shown in red, where the holes that you see are due to regions that we needed to mask because of the presence of halos due to very bright stars. Superimposed, you can see the same field as imaged by X-ray observatories, that is XMM Newton and Chandra. As for the CDFS, there is only a small region which was surveyed in the X-rays very deeply. This means that only a small percentage of the sources in our sample has an X-ray counterpart. Conversely, there is a very good superposition, very good overlapping with data from other other optical and infrared surveys. So you can see here, for instance, data from Swire and Search surveys. Wow, that's nice. Okay, so our analysis consists in defining a sample of optically variable sources. So we define a variability threshold, which you can see here in black as a solid line, and all the sources above the threshold are assumed to be variable. The dashed line here represents the average RMS of our sample of sources, which only includes those objects which are detected in 20% of the epochs at least, in order to reduce the number of contaminants. And we also required that our sources were brighter than the 23rd magnitude. So here I show as an example the light curve of an AGN with its typical red noise, that is variability increasing with longer baselines, and the light curve of a supernova with the typical peak, the bump, and the plateau, due to the emission, where the emission from the galaxy dominates. Our analysis also consists in comparing the results that we obtained from different techniques. I mean, every technique has already been tested, widely tested, but what we did is also to see how, if and to which extent, the results of the techniques overlap. So, since the cosmos field was surveyed by most observatories, we could cross-match our catalog of variable sources with data from the X-ray observatories. And what we found is that 3/4 of the sources have an X-ray counterpart. And they also have, all of them, an X-ray luminosity higher than 10 to the 32 Hz per second, which is generally assumed to be the threshold for to select AGNs. Moreover, all of the sources with an X-ray counterpart have an X-ray to optical flux ratio, which is shown here, ranging -1 to 1, and this too is typical of AGN. Here you can see between the solid lines the stripe where AGNs usually lie. I should also say that 24% of the sources do not have an X-ray counterpart, but most of them, all but 3/4 sources, turned out to be supernovae, so it's no surprise that they don't have an X-ray counterpart. As for the comparison with the diagnostics based on colors, I report here a color versus color diagram where the colors I use are Z minus K and R minus V. You can see that objects tend to occupy two distinct regions depending on their nature. So there is a stellar sequence here, and the area occupied by galaxies here shown in violet. But it is also apparent that there is a different class of sources which are optically variable, X-ray emitters. You can see them marked by crosses since we confirm them as AGNs on the basis of their X-ray properties. And they are also extended as for their colors, but compact if you look at their stellarity index. Okay, so it is very likely that these sources are a different population of sources, that is, quasar-like AGN candidates. Okay, this was just in case the first picture wasn't good enough to see. Okay, here I show one of the most widely used diagnostics in the infrared. This is another example of color versus color diagram. It was used by Lacey and collaborators in several works, and they define a region which is defined here by the solid line, where AGNs generally place themselves. It is worth saying that this same region was tested in a later work by Donnelly and collaborators, where they made simulations taking into account galaxies with a growing and growing component by AGNs. And they found that the higher the AGN component, the more the sources tend to be and evolve inside the AGN area defined by Lacey. And we can also see from the last figure on the bottom right that when the AGN contribution is very high, objects are in a smaller region, which is the one that you can see here, defined by the dashed lines. AGNs in this area are also generally X-ray emitters, I mean with a high X-ray emission. So this is one more diagnostic that we could use. And in this case, also in this case, there is 64% of our sources in this area. Oh, I forgot to mention that in the previous diagram, 65% of our sources matched the color criterion. So we always have a quite good overlapping with results from other diagnostics. There is also a work by Shu and collaborators where they classify sources on the basis of their spectral energy distribution. And I would like to say that for all the sources which have a counterpart in that catalog, in that list, there is a correspondence between their classification and our own classification, which is based on light curves. So every time that we classify a source as an AGN, we found that they had classified the same source as an AGN as well on the basis of their set. So here you can see the dots which represent the data at our disposal, while the red line shows the best fit template, and the gray line here is the best fit corresponding to a star. So this is an AGN spectrum, AGN fitting, while the other object is not clearly an AGN. In both our works, we reach a very high purity, 94% in the case of the Cosmos field, 85% for the CDFS. We cannot say the same for completeness, but we know why this happens. We performed some tests, and we show that if we had a longer baseline, say a 2-year baseline, variability increases up to 50%, intrinsic variability. So if we had data over a longer baseline, we could have a larger sample of optically variable sources and hence a higher completeness. We also show that if we take into account only sources with in our sample having an X-ray counterpart, it turns out that their average variability, optical variability I mean, is higher than the average variability of the whole population. In the first case, the average element is here, the blue line, while in the second case it is represented by the red line. This means that on average, X-ray sources are more variable than sources without an X-ray counterpart. And so, even though most of them, 85% of them, is below our threshold, a lower threshold will return a larger sample of AGN candidates and again a higher completeness. So the question is, how can we obtain a lower threshold? Well, we have been highly conservative throughout our work, since this was based on data from the very first period of activity of the telescope, but we can properly lower the threshold, being less conservative, so there will be more contaminants, but we will also have a larger sample of AGN candidates, and this is one of the things that we plan to do. We also want to perform again our analysis over new observations of the Cosmos field which are to be made, and on the extensions of the CDFS observations. And of course it would also be interesting to repeat our analysis onto data coming from current and future surveys. Okay, I think I'll stop here. Thank you for listening.
So, thanks Demetra for the perfect time. Other question? Please. Andrea, you start.
So, this is very interesting. You said that 2 years is a good timeline for this. What is the best cadence? So, what is the time between the observations that you would ideally want in order to detect AGN?
You mean observation? If we had 2 years observation, a 2-year-long baseline?
Yes, basically over, let's say, over 2 years baseline, how many observations, how many epochs would you ideally want to observe?
Well, in our case, we had observations every 3 days, even though we have a whole of a month and a half in our baseline. But I guess it's not a matter of how many times, but how long you can observe. Of course, if we have 2 observations, it's not a good thing for our analysis. But even in our case, we had I dealt with 27 epochs, for instance. Okay, but even though we had I guess 50 epochs over 2 years, it would be good for our analysis. There are works in the literature, for instance, by Dario Treves and collaborators, where they have a 2-year-long baseline and only 8 epochs. Okay, and they perform a similar analysis. So I guess what is important is how long the baseline is.
Yeah, so I mean, mainly the point is what is the minimum you can deal with to use something like dark energy survey, and where you can't,
The minimum number of epochs, you mean?
So that's why I was asking, but so maybe like to eight.
Yeah,
epochs,
they had 8
use
epochs,
like
only 8,
feasible.
yeah. So I guess we could, with the same number at least.
But you said at the beginning you had, so the X-ray detected was the majority of AGN, then you had 24% left,
Yes.
of which you could exclude a certain fraction but not the total.
No, not the total.
Exactly, so what's the rest?
Yeah, there are 3 sources without an X-ray emission, but they turned out to be AGNs on the basis of their color diagram. You can see here marked by, you should see here, them here, marked by the boxes. Okay, only 3 sources. And then there are supernovae and 3 more sources which do not have a counterpart in any catalog. Okay, this is really weird. We are trying to investigate this. Maybe Mauricio already told you about this, because they do not have a counterpart in any of the Cosmos catalogs I investigated so far. And we looked at them onto images, and they are really there. Okay, so they are not fakes.
But they were not there before. In the HS image, they were not in the
Yeah,
image.
and
They came up later.
So you're discovering something.
maybe.
Could you please briefly flash the 2 SCD? One was the AGN and one was not an AGN.
Oh, yes,
How
sorry.
they look like on the overall SCD?
This one you mean?
Yeah. And you have you have on the x-axis is lambda. What is the stand there?
Yeah, this is lambda in micron, while this is the magnitude. This is from a work by Xu. Yeah, essentially the red line here indicates the best fit template. There are numbers here corresponding to different objects. For instance, 27 here is a number indicating an AGN, because numbers from 19 to 30 are dedicated to AGNs. While in the other case, number 3 indicates a normal galaxy. There is a legend, of course, to understand the plot.
These work are important to get a statistic on the effect of the full multi-wavelength data. In Euclid, we are trying to understand how wrong we are in the physical properties of galaxies when there is a hidden AGN, which is not a new problem, but it's becoming severe when you have to analyze this amount of data.
Yeah, I bet.
And so we need the statistics of well-sampled SCD at different redshift for various types of AGN.
I see. Well, this is based on a work of Mara Salvato, previous work of Mara Salvato, 2011.
Yeah, Mar is very negative though, so I try to stand for positivity. Every time we talk, she said there is no way, we'll never understand.
Oh, great.
Okay.
There's Diego waiting for me here.
So, 2 brief questions. One is, what is the minimum set of filters that you will need for doing your job here?
The minimum set of filters?
Yeah, for doing your selection, for performing the SCD, because I guess you want the optical part, but you also need near infrared, so you have to go for fields where you have multiple coverage, multi-wavelength coverage.
Wait, I'm not sure I understood, because I only use R-band data. Then I need several filters, I need other data in order to compare my results with them. So I'm not sure what you mean.
So you're doing your selection using optical filters.
Yeah.
But then at some point you also checked against near infrared filters.
Yeah, but these are data from other surveys.
Yeah, so do you need them also when you want to extend to other surveys?
Yes, of course, if I want to make the same comparison, I do. But since I showed that there is a good overlapping between the results obtained by means of different diagnostics, I can state now that if I only had only optical observations, 80% of the sources are very likely to be AGNs on the basis of results that we achieved.
And I see that you also estimate the photometric redshifting, despite you have a spectroscopic one. Am I right from this plot?
Here?
Yeah.
Yeah, in this case there are spectroscopic redshifts available. In the case of the Cosmos field, photometric spectroscopic redshifts are available for most of the sources too.
Okay, so my question is, have you tried fixing the spectroscopic redshift and repeating the feed?
Oh, you mean using spectroscopic redshift? Yeah, this could be done, of course. We did not think about it so far, but we could.
Okay, thank you.
Thank you.
Okay, let's thank.
Oh, I guess there was one more.
One more? Excuse me. I'm sorry.
I just wanted to ask, how many of your variability candidates would you not have picked up with simple U minus G, G minus R below redshift 2.2?
Pardon, I didn't get you. How many of my candidates?
Would you have picked up just using color, traditional UVX color selection?
By means of color selection, I will find about 60% of the sources. Okay, UVV colors, or as well as the color selection I use here. I tried several diagnostics. I didn't show them all because most of my sample was validated, so there was no need to show everything. Okay, but it's around 60% in any case.
So the other 40% were high redshift?
No, they sometimes there is no counterpart. They are just all of my sources are below redshift 3.
Right.
Okay, so if you have to stop about around 2.2, it's almost all the sources here.
So they're not UVX, is what you're saying. Some things you pick up are not UVX.
I did not separate sources into redshift bins. So if you want to know about
we can talk.
Okay.
Okay, thanks Demetra.
Thank you.
And now we switch a bit subject. Andrea De Luca will talk about the Extras project, exploring the X-ray transient at variable sky.
Good morning. I would like to thank the organizers for giving me the opportunity to be here and to speak before an audience including astronomers from fields different from my own. I will talk about a project which is based on a large sample of X-ray observations, and I hope to stimulate your interest. There are three keywords that can summarize the rationale for the Extras project. The first one is variability. Almost all astrophysical sources display a characteristic variability in flux and spectral shape on a specific time scale. And the study of this variability can give crucial clues about the nature of the sources and of their emission physics. This is especially true in the high energy range of the electromagnetic spectrum. The second keyword is serendipity. Focusing on the soft X-ray range from 0.1 to 10 keV, each day focusing X-ray telescopes collect a very large amount of data about serendipitous sources that fall by chance inside their field of view. Since each detected photon is time-tagged, there is also a lot of information about variability of those sources, but this information remains mostly unused in data archives. The third keyword is XMM Newton EPIC. The European Photon Imaging Camera, on board the XMM Newton X-ray Observatory of the European Space Agency, is the most powerful tool to study the soft X-ray sky. It has a beautiful combination of large effective area, good angular, spectral and temporal resolution. It also has a pretty large field of view, and as a demonstration of the capabilities of EPIC, you can see here a movie produced using the very deep observation of the raw future molecular clouds. You can see here a lot of sources displaying a spectacular variability, popping up and disappearing. They also change in spectral shape, which is seen here as a change in color. Most of these sources are young stellar objects, since the field is a molecular cloud, which is a star-forming region. The XMM Newton satellite was launched in 1999. It is still operational, so there is a very large database of observation which is available. Extras will perform possibly the most complete and sensitive search for variability in the soft X-ray sky. We will systematically explore all the time-related information included in the whole EPIC database. We will extract this information and we will release it to the community in an easy-to-use form. And the goal of the project is to allow the community to extract more science from XMM Newton data. The project was funded by the European Commission to complete the task in 3 years. The expected end of the project is 2016. This is our consortium. This is led by INAF, and it also includes 5 other institutions in 3 different countries. Let me start by a short reminder about the statistics of the EPIC database. This is the sky, and it is projecting the galactic coordinate. Each green dot here is a pointed observation with the EPIC camera. There are more than 10,000 pointings. Each one covers a field of view as large as a full moon, lasts between 5 kiloseconds, let's say 1 hour and a half, to 130 kiloseconds, let's say 1 day and a half, and includes data about lots of serendipitous X-ray sources, as you can see here. Soon after the launch of the XMM Newton Observatory, the European Space Agency funded a consortium of institutions called the XMM Newton Survey Science Center in order to generate a catalog of serendipitous X-ray sources and to release it to the community. The most recent release, called the 3XMM catalog, includes data up to December 2012. It covers about 800 degrees of the sky and lists about 4,000 sources related to 500,000 detections. About 70,000 sources have been detected more than once because of the overlap, which can be either fortuitous or planned, between different observations in different epochs. This is the largest and most sensitive X-ray catalog ever compiled. In the same image you can also see these blue lines, which are slews. While the satellite moves from one point in direction to the next one, data are collected from the portion of the sky which is scanned by the X-ray telescope. This allows to extract images like the one you can see here with an exposure time of 10 seconds. The combination of all of this blue data covers a very large fraction of the sky, and 25% of the sky have been scanned more than once. Using this data, a catalog of about 20,000 sources have been produced. This is the so-called slew survey catalog. The sensitivity is pretty good, since in the soft range from 0.5 to 2 kV, it is almost as sensitive as the Rosatov sky survey. What has been done so far in order to explore the time domain information? Time domain information has been mostly neglected indeed. This is the fundamental count rate in the EPIC cameras versus time scale plane. During the production of the 3XMN catalog from pointed data, and considering short-term variability here, short-term variability means variability on a time scale which is shorter than the one of the single observation, so variability within an observation. During the production of the 3XMN catalog, a light curve with a uniform time beam was extracted for brightest sources which lie in the blue region in this plane. A basic variability test was also performed. You can see that there is a very large portion of the plane which needs to be explored, and this will be our task. Extras will also characterize for the first time the X-ray variability of all detected sources across the whole of the plane. So, still considering short-term variability, we will have 3 different lines of research: a periodic variability, periodicity, and the search for new transient. We will consider all of the detected point sources, and we will extract the light curves for each of them using both a uniform and a non-uniform time beam, using, for instance, the Bayesian block approach. We will also extract a power spectrum for each source, and according to the number of counts, we will perform the job in one or in more than one energy range. Most important, we will compute a set of parameters that describe different properties of the time behavior of the source. For instance, starting from the light curve, we could compute the fraction of the time spent by the source at more than 3 sigma from its average country. Or starting from a power spectrum, we could compute the frequency range within which a certain fraction of the total power is. About periodicity, we will search for pulsations in a very large sample of sources, about 300,000. We will use, to perform this search, every single time of arrival of each detected photon, which allows us to achieve the maximum sensitivity. This is a power spectrum of a source that a preliminary version of our pipeline unveiled to be a pulsator, a 95-minute pulsator, and you can see that the same behavior is not seen when considering the light curve, the beam light curve, which was provided for the same source within the 3XMM catalog. For each detector pulsator, we will give the value of the period, folded light curves. We will also compute upper limits to the pulse fraction for all of the sources in the catalog. An interesting line is then the search for new transients. We will search for all sources that raise above the detection threshold for just a small fraction of the observing time. Such sources are not detected by the standard source detection, which is performed, for instance, for the production of the serendipitous source catalog, because they are buried under the background in the full integration. This is a first example of a detected transient by our pipeline. I will talk about this later. For each transient, we provide the position, the light curve, and constraints on the spectrum. Coming now to long-term variability, which means variability between different observations of the satellite. As I've already said, there is a lot of sources, both in the serendipitous source catalog extracted from pointed data and for sources in the SLU catalog that have been detected more than once. This is due to the overlap between different observations at different epochs. There is also another possibility. We can compute an upper limit to the emission of a source using an observation that imaged the same field but did not detect that source. The dataset spans a very long baseline, more than a decade, and it is quite surprising that no systematic studies had been performed so far. This will be our job. We will combine all flux measurements for all sources. We will compute for all sources upper limits using all available data, and we will produce long-term light curves spanning possibly more than a decade for some source. We will use such light curves in order to search for variability, and we will try to characterize variability on them. So far I've been describing the X-ray data analysis lines, which are here, and this is not a complete view of our project, since we will also have a multi-wavelength characterization for all sources that we will detect by the transient search. Then, most important, we will perform a phenomenological classification of all sources. We will use as an input to our automatic algorithm a set of features that include parameters describing the temporal behavior, parameters describing the spectral shape in X-rays, but also contextual information from multi-wavelength archives. All of our results will be released together with products and new software tools in a public archive at the end of the project, which is expected to be at the end of 2016. Coming to science, as I've said, the goal of the project is to allow the community to do more science. And in this plot, I've shown the peak X-ray luminosity as a function of the variability time scale of the most prominent X-ray emitters. The diagonal lines mark the approximate sensitivity of our search for different distances. And as you can see, there is a very large discovery space that can be opened by our systematic analysis. Indeed, there is a very large number of science cases that can be addressed by our results or that can benefit from the results of experts. These range from the search and characterization for rare events, for instance, supernovae shock breakout bursts, or peculiar gamma ray bursts, or tidal disruption events. But of course, there is a number of science cases covering almost all topics in astrophysics, from extragalactic sources, AGNs, blazars, ultraluminous X-ray binaries, to galactic sources, of course, X-ray binaries, cataclysmic variables. We expect to detect 10,000 stellar flares, for instance. We also expect to detect new members of the isolated neutron star family, for instance, new magnetas. We also hope to set some constraint on the sources that are seen to emit the so-called fast radio bursts, which have been very poorly understood so far. I will conclude by showing to you a first result that has been made possible by a preliminary version of our pipeline. This is a very faint source in the 3XMM catalog. It is barely visible inside the circle. This is a 120 kilosecond observation. If you go to a very smaller time scale, you can see that the source is clearly detected. Indeed, this is a transient, and its position is coincident with the one of a known young stellar object. This is a zoom of a portion of the light curve. We detected about 25 photons in 40 minutes, and then, using all the available observing time, which is for the 4 days of integration, we detected no more signal. So, this is indeed a transient, and the emission is consistent with being a stellar flare. This event turned out to be quite interesting, since there are indications that the young stellar object coincident in position with the flare is a very, very early protostar, an object of the so-called class 0 young stellar object. This is interesting because it seems that X-ray emission for this kind of sources is very poorly known. Indeed, this is one of the unique episodes of X-ray emission ever detected from such a kind of sources. This is still a work in progress, but this is of course a demonstration of the large discovery space that can be opened by our systematic search. I will conclude by showing to you a list of contacts. I'm the coordinator of the project. These are the names of people leading the teams in different partner institutions. These are the names of the leaders of the different research lines within the project. For more information, you can visit our website. And if you have comments or suggestions, or if you would like to cooperate with us, you can contact us, of course. Thank you.
Questions?
How many AGNs have you already seen?
I think that no one has ever computed the number of AGNs in the whole database, but we have 400,000 sources. I believe that a very large fraction of them could be AGNs. The problem will be to identify them, of course, using X-ray variability together with multi-relevant information. Possibly most of them will be at least tentatively classified, so possibly more than 100,000.
Do you plan to give some releases before to
plasma 16, partial releases?
Well, we are running sort of early analysis using a simplified version of our pipeline, and according to the results, we can consider the possibility of maybe releasing to the public some partial views of our project. This is still under discussion indeed. In any case, if people is interested in a specific class of sources, or if you would like to suggest some specific analysis, I encourage you to contact us in order to keep in touch with the team. We are still working on the data, and the data analysis will end at the end of next year, so there is still plenty of time.
Especially if you want to provide brute force work.
Yes, of course, work is well accepted.
Okay.
In which terraforming region did you detect this class 0?
This is in the refugee cloud. This was one of the fields that we selected to run a preliminary version of the transient search, still in the proposal preparation phase of the project. And we immediately detected this episode, which at the time was not included in the XMM serendipitous source catalog. And our colleagues within the team, which are experts in stellar flares, people from Palermo, from the Palermo group, immediately said that this was possibly a very interesting case. We are now working on this, and I hope we will get out on a paper very soon.
Okay, I would say that we can thank Andrea and welcome Enrico Capellaro, who will be talking about supernovae as cosmological probes. Ti do un warning quando
Well, it is really a pleasure to be here because I have the best time, I think, to thank you, Massimo, for the opportunity you gave me a few years ago. First, to contribute a small contribution to the VSP project via the Omega Cam consortium, and also for the possibility to do the science then with the VST. It took a bit longer than we hoped or expected, but the important point is that we are getting to the results. You have seen some of the results yesterday with Maria Teresa Botticella, and so I think this is what we get now. I was given the talk the duty to talk about supernova as cosmological probe, and you know that the story of supernova, the link of supernova with cosmology goes back from the very beginning. Actually, very early on there was almost confusing things because the people say when they didn't know what the supernova were, they say it is impossible that the galaxy are really so distant, or the nebulae were really so distant, because if that is true, the novae inside there will be impossibly great absolute magnitude. And the truth was that they had indeed this great absolute magnitude. Talking about supernova and cosmology link is go from in many different topics, and I choose to basically neglect what I'm most interested in, stellar population tracer. There has been a talk by Maria Teresa. I think most of the effort in the last years has been on this, and I need to acknowledge these things, the supernova as distance indicator. And about the supernova also probe fundamental physics in many different contexts, and there will be a talk later by Lino, which will show what can happen next. So just two slides for this, I say I neglect, but two slides I will put on the power of supernova's population tracer. This is a plot of the core collapse supernova rate, type 2 and type 1 BC, as a function of the mass of the host galaxy, per unit mass of the host galaxy, and as a function of mass. And you see this nice, very well relation, trend, where the galaxy with high mass has less supernovae per unit mass. The axis here can be immediately translated to the specific star formation rate for core collapse, because they are directly linked to star formation. And then the interpretation of these things come out naturally. This is the downsizing effect that is seen in galaxy. Galaxy with higher mass have a lower specific star formation rate. And you see, it is very well traced, and you just need more statistics, and you can explore these things in Redshift. And it works the other side, because this is a plot of the same things, but for type 1a supernovae, of which, let's say, we do not know really what are the progenitor. The fact that they show the same trend means that they are linked to the specific star formation rate, so a good fraction of type 1a must come from a relatively young population. In the last few years, beginning with, I began interested in the VST because I want to basically populate this plot, which is a plot of the supernova rate. This is for type 1a, but I'm interested also in core collapse as a function of redshift. And when the VST was starting to be built, these were the measurements available. We took some longer to come, and this is what we have now. So it seems, but I take this as a good thing. If most people work with this, it means it is interesting. And so it's something is still worthwhile to work. Then go to the main subject, which is supernova as distance indicator. We know the story of Hubble constant. For the supernova, there was a huge value early on, then the things converged, but then stopped to converge at some point. And the spread remained for many years between two groups. And, for the supernova entered as distance indicator, as a measurement of the Hubble constant relatively late. The first attempt which I could find is in '74, is a PhD thesis, almost forgotten. And then the real action began here in the early '80s with the two groups using supernovae and producing the typical discrepancy. I must now show you that we have done something with Massimo della Valle, Rosino at the time. We did use the supernova, the compared novae in our galaxy and in Virgo, and supernovae in Virgo and Coma cluster, to give a value of the Hubble constant. Became 70, but strange results. And notice also that we had an error which was twice as many as the other, which go through all the year. Now, where this came from? Where we got this result? Well, we had a careful account for extinction of the supernovae through a simple prescription. We compare the color at maximum, assume that there is a relation, we know that there is a relation between color excess and absorption, and we can derive, so the absorption is corrected. At the time we came out with an heretic idea, based on the fact that the dispersion along the Hubble diagram was reduced if we change the value of the RV. Reduced but quite a lot. This you see as how much we need to reduce to decrease the. And I must admit that starting from here, it was completely ignored by most people. And indeed, a few years later, Sanders and Taman published a paper where they wrote supernova standard Cardinal, the existing dispersions are usually low, and is due to observational error. It's not intrinsic. And the color is at maximum is this, and there is no evidence for an unorthodox value of the ratio of the RDV. And they come out with a value of each 47. Now, that there is difference between type 1a was not well before, 20 years before. Again, a paper was many group, but also in a paper by Barbon, Capaccioli, Ciatti, they say, well, there is a separation between fast and slow, but we are not able at this time to see if there is a difference in magnitude between these two classes. And someone later was able to see this. You can see here a plot by Mark Phillips and Maria Mui that found a very good correlation between the velocity evolution, the luminosity evolution, and the absolute magnitude. What made the difference? The difference was that they had CCD photometry compared with plate. They could separate 1A from 1BC, who were not known at the time, and they improved the extinction correction. The improvement, and based on this, you have a view of how things go. These are a plot of light curve of type 1a, a lot of them, and the color, they are coded with the color, which the black are the one slowing decline, and the green the one faster declining, and you see that they separate in magnitude quite well. And the range is not the 0.2 or less of Taman, but 2 magnitude. About extinction correction, we, as I say, at the time we used the color at maximum. Some time later, it was shown that it is better to use the color, say, 30 to 40 days later. These are a bunch of color curves, which seem quite crazy, but then if you match these, you can find that they match very well in this day. And instead at maximum, the dispersion remains sometimes. So if you want to correct for extinction, it's better to go here. And what about the RV value? Well, it was neglected, but then it came out again. And if you look to, there are 3 papers just this year, which found an RV much less than the standard value for the galaxy, which is strange, but it's come out from the data. And there has been people trying to find out what could be a possible explanation for this. And what would be most simple is to admit that the dust is very nearby the supernova in dense cloud, so you have multiple scattering in some of this cloud. And also, you add to this that the dust can be different, may have been produced by stellar evolution, so it may be different nearby supernova. But there is a recent work also by Nando Patato, which using spectropolarimetry, that because if the dust is really so close and so dense, you should have an effect on spectral polarimetry. You don't see this, so it doesn't seem to work. But we don't have an explanation, but this is a very confirmed result that for supernovae, the RV is significantly less than for the average of the galaxy. So these were the value at some point, and then the things really changed when Cepheid is coming for calibrating. And so this is a plot of the Hubble constant as a function of time using only supernovae. This was the Pacioli 90 point. Then when the Cepheid comes, at the beginning they didn't reduce at all the dispersion, but some work was done, and we also here, working with other people here, Marcella Marconi, Giuliana Fiorentino, Ilaria Musella, we used, combined their experience on Cepheid, my knowledge of supernovae, produce a new value of the Hubble constant here. You see, it's identical to the value in 90, and we decreased by half there. After that, there's been a lot of work, and you see that now they think that the measurement cluster, there's another other point which comes from the group here in Naples, which seem to go to a somewhat higher value than the 70 comes out around 76 or so, 75. However, this is the last Planck results, which instead go the other direction. And you see the error bar become again to be not compatible one with the other. And so this is the well-known tension of Planck with supernovae. You know that the two probes have different systematics, different things, but at the moment there seems to be a slight inconsistency, let's say. Then go further. We had a Hubble constant, and in the early on, already in the late 70s, there was this idea that if you could measure supernova at very high distance, you could have a measurement of the density of matter in the universe. You were intended to measure the deceleration. That could be negligible or could be very large, depending on how much matter you have in the universe. And the people make some computations, say you need a space telescope for this because you need very far and so on. And these are just a well-known path, let's say, to the Nobel Prize. The first attempt to find supernovae, a significant redshift, was done, with the Delitzsch 1.5 meter telescope. They found one supernova 0.3. Then the two groups which came in the competition, they found the first supernova redshift around 0.5 in mid-90. First report that omega matter must be small because we don't see deceleration. And then at some point, actually, we see an acceleration. Late, this story very well. So these are the original plots. The compilation of the original data of the two groups put together, which is, I like it because it shows the dispersion of the point. You see the effect that was measured is a small effect, but significant. And here you see one very important point is that the supernovae alone cannot measure omega mater and omega lambda. You need another constraint. Here, the constraint is that the universe is flat, and which then put you in this situation. And so these were the results which were around for some time. The supernovae, after that, other supernovae has been collected, and this is a collection, basically, the two sample which list basically all the useful data available. You see there is some dispersion on this axis by all these different contributors. I like this other way to show this, in which you use only basically three samples, four nearby supernovae, Sloan, Legacy, HST. It looks much better. Less dispersion, and this is one thing that you need to understand. The systematic between different surveys can be very important. So the results confirm that everything is consistent with the cosmological constant. There was an attempt also to see, let's go a bit further and see if we can see an evolution of the omega mater, omega lambda, and this work of Sullivan, very nice work, shows that you are consistent with no evolution, but the best, in principle, the most high probability for some evolution, but let's see, that the Planck recent result stress again, no evidence for dynamical dark energy, so which is consistent at this level with the supernova. So what next? We need to understand these things better. We need to improve the jargon now. We have the figure of merit, which is basically the error which you measure the parameter of the equation of state. You need to improve that by a factor 10. And there was groups studying how to do this, and the conclusion is that all four principal techniques, baryonics, oscillation, cluster survey, supernova lensing, should be done at the same times to get the required precision. So supernovae are still needed. What do we have to do from the side of supernova? We have to increase statistics by 1 order of magnitude at least, and we have to reduce the systematic by also about 1 order of magnitude. Systematics, I will talk about survey to improve statistics later, but systematics, to reduce systematics, we have to improve the calibration and to possibly constrain evolution, because, you know, if there is an evolution and to constrain evolution, you can study how the supernova population change with cosmic time, or try to figure out better what is the physics. There has been a huge effort by many groups to try to understand the physics of supernova, with more or less success. I take only one example, which is from our own work. The early 19, there was this idea that the supernova have a one parameter family. One parameter described the evolution of the type 1a supernova. In this work, Stefano Benetti shows that instead there is at least one other parameter. This is the plot of the delta M15, which means basically luminosity. Let's take this axis luminosity. And this is a gradient of expansion velocity. And there are groups here which do not correlate, so there is some other things going on. The interesting is some year later, in another work, we found that if you look, this was the ejecta, very near maximum. This is the inner nebula, very late after maximum. And there is a shift in line. So there are objects which appear to be blue shifted and others which appear to be red shifted. And the two things have some order. How you explain this? Well, the idea is that you can explain if you have an off-center ignition of the explosion, because then, I have not time to explain, but what you see depending on the viewing angle change. And that would be very nice for cosmology, because there is no intrinsic evolution, you have just a viewing angle, and statistics can help with that. I must admit that, this likely can explain some of the variance, maybe 60 or 70%, but some variance remain which we cannot explain. However, I would this is an advertisement, we have work which is going on in Europe to try to understand the physics. There are these, I hope, well-known PESTO survey, which is done at ISO. Now there is going on this, Gaia is producing alert, supernovae, which we are trying to follow to figure out things. And for the future, we are thinking to an instrument, which is SOX, Sonovic Shooter. And this Georgopoulos the first day told me, what we know, but it told very well that the bottleneck of current diffusion transit is follow-up. We know this, and so in March this year we made a proposal for a response to the call of idea for the OVISO, for an instrument to be put at the NTT, and we are looking to have an optical infrared spectrograph for follow-up of bright transient. And not only transit, much more. And we are now preparing a tailored proposal which needs to be submitted by February next year. So, just a few rapid words on future survey. We had the description of what is going on just now, that is the dark energy survey. You know, the figure of merits we have from the Sullivan work was about 10. The figure of merits which come out from here can grow already by an order of magnitude, 100. I don't need to describe this, it was described the other day, but I go, one point I want to make is that if you really want to go higher redshift, you need to move in the infrared. Supernovae 1A are blue objects, we do not emit in the UV. So when you move in redshift, at some point you lose, even with the HST, you cannot go farther because this is the maximum magnitude, but then you need to follow the light curve to calibrate, so you cannot do this. While if you take the H, this is how it changes the H-band absolute magnitude as a function of redshift. You see, here is where you get with VLT. If you can go down, if you can go down well, it has come out, but if you can go down by two magnitude, you can follow basically type 1a supernova for up to redshift 2 or even farther. So what you need is a wide field infrared imager in space, because from the ground you cannot go as deep. VLT cannot go deeper than this. And you can go deeper, but on much smaller field, not on a wide field. It is unique for search. So there was the right instrument for this, which is Euclid. Euclid was not taught at all to do supernovae. The idea was to do weak lensing and baronic oscillation. These were the main probe of Euclid. But it has the proper instrument on board, so we try to devise a strategy which can use the instrument. We basically, let's say, make the proposal. It's not yet a formal proposal. At the moment it is a paper, it will become a formal proposal in due time. And in this paper, which is done with other people inside, I see one co-author coming in, we show that with this survey, which is called Desire, because we really desire to do this, we do not know if we can do, we can add quite a significant fraction of supernova redshift up to 1.5. This will need to work with LSST, and this will provide a figure of merit only for supernovae, which can go up to 200, and then combining with the other, of course, much better. We know, of course, that there is the other side of the Atlantic working to a mission which is the first. It is a much larger mirror, so they can afford to do spectroscopy, and they indeed include in their program, they have a survey for which is intended to produce 2,500 type 1a supernovae, basically the same redshift range up to redshift 1.7. I mean, it's in very good shape, but not yet approved, so let's see what happens. And finally, just to say what beyond type 1a supernova. Type 1a supernova cannot go farther than redshift 2, but there are objects, supernovae, which can go much farther. This is a recent discovery. You see, it is the paper summarizing things just a couple of years ago. There was a discovery of a population of extremely bright, what we call ultra bright, super luminous supernovae, which are 100 times more luminous than type 1a. Still do not know where they are coming from, but certainly they are massive stars. And there was a report, I do not comment on how much I believe this, but there is a report that they have discovered that this object up to redshift almost 4. You can see individual stars are redshift 4. And there are, I mean, what they have very interesting is that they are bright, long-lasting, because the light curve is slow. They stay bright for 1, 2, 3 months. They have a strong UV, so that you can find, and the other side, they are quite rare. There is about one supernova of this type every 1,000, 10,000 standard core collapse, and they are unknown. We do not know what they are. But still, there have been people trying to figure out if they can be used calibrated. The plot here looks very nice. I must admit that the measurements are still far too low to really think if we can use a distant indicator. And there is other things which seems to me more sure that we can do this. You can distinguish the EMF, a redshift, well, here they claim up to redshift 14 using, they make an estimation using JWST, counting the number of core collapse, standard core collapse against this superluminous kind of object. So I think we have still a lot to do work. I was used to think that there was not much more room to do with supernova. I still think there is much lot to do. And so I finish here.
this? Please.
Actually, one is about Euclid. So you are shown limited magnitude you need is 2024.
Yeah.
I'm afraid Euclid doesn't go much deeper than that.
You know that we have a strategy which require longer exposure time than the standard exposure time, which I know is a difficult thing to implement, but we work it out, and we only use the infrared section of this.
The real question is about one of the two first slides when you compare the supernova rate with the specific star formation. Can you show again the slope? Because
yeah, I know. It seems
flat actually. So the slope you have is quite steep. So.
This comes from a paper of Wei-Dong Lee, 2011. This is the loss supernova search. I think that here you need to account how they measure the mass of the galaxy. That's, I would say, is the main problem for these things, because you know better than me, the measuring mass of the galaxy, you need information, and so they took the K-band magnitude and translated using color, B minus K color, and they got the mass. And this is what they come out. The statistics is good. I think that the paper they don't even mention downsizing as an effect, because they didn't think that. I do not would stick to. This is a local universe. Yes, there is some plot higher redshift, but still not many measurements.
Your historical remarks were very interesting. It was, of course, great to see that yours and Massimo Capriccioni's values were bang on already such a long time ago. But I think what was really impressive about that measurement was the large error bar. In the sense that you seem to be more capable of producing realistic error bars at the time than others.
I think this. I was very proud of that at the time. Because all these people, we are. Let's say the other direction. We agree with both people inside 2 sigma.
So in fact, I think you were right also more for that reason almost than the fact that you were lucky to be being on.
Absolutely.
But what I want to get to is now you show the tension between the current Hubble constant results and WMAP. And again, so this
Planck actually. Planck.
Planck, sorry.
Yeah.
And this reminds me again of this tension that was there in the 1980s. And so I wonder again here, doesn't the field really have a serious issue with error bars?
I think so.
Rather than collecting more and more data or trying to, I know people are thinking about this. I'm not saying anything new really, but shouldn't people invest more in trying to get proper error bars and thinking about whether tensions really exist, or I guess error bars are really.
The comment I can make from the Planck side is that since it's a fit with the 10 parameters, or no, more than that, and that's you come out with something which is very difficult, I think, to estimate error bar. With the supernova, you include what you think, but I also believe there is a tendency to not showing something which should be added to the. Yeah.
But in any case, the old saying that cosmologists are often in error, never in doubt. Hold. Okay, Massimo.
Yeah, but I'm happy to give the word to Massimo.
Go ahead.
So I certainly think supernova science in itself is extremely interesting. Instead, for cosmology, every time people show this fantastic Hubble diagram, the one that you showed in the first survey, I wonder why do we need more data to place in a diagram that is so extremely well defined, at least up to redshift 1.4. And you discussed the problematics that we have an entire redshift. So, because this is sucking away most the money of the funding agency to probe these 4 things, and I would like to understand why, even if the error value is becoming visible. I wouldn't learn something.
The point is that it is good but it's not good enough to distinguish the models. But this is true. Is true. You point to supernovae. I may agree with you, but it's true for all of the other. So the need to reduce the figure to increase the figure of merit by 2 orders of magnitude to see if there is evolution. It means basically that you need to have a good sample for any redshift bin. I think that if you really want to make a step further in these things, we really need to have a better. And for supernovae, the point is, if you want to work on supernovae, either you increase the sample at least 10 times, otherwise increasing 10% doesn't make any difference. So you need to make a big jump in any of the possible probe.
Well, just a memory concerning the historical tension. I was in Texas at the time of the fight between the Vaucouleurs and Sandage. And one morning I got to the office and the Vaucouleur was very upset. He had a letter in his hands. And he said, read. I read the letter. The letter was a technical letter written by Sandage, which ended this way. Every morning before going to work, I go to church to pray God that illuminates you.
Okay, I guess we can thank Enrico and all the and we reconvene. What time? 2:30?
Yes.
Here it's 2:20, I guess. We can compromise for 2:30.
Just to mention, we are preparing for the conference proceedings. So they're going to be published on Astrophysics and Space Science Proceedings volume. And the deadline for paper submission will be February 15 next year. And this is the tentative distribution of pages for the different kind of contribution. So we hope that this will be reference papers. So it's good for young people, particularly, to have their paper submitted and very well written. And of course, we invite also the invited speakers and with review and target papers to submit their contribution. We will thank everybody for that. Okay. So let's get to lunch. See you later.